Good afternoon. My name is Hermine Nalbandian, and today's webinar is on trace elements in coal combustion, based on the IEA Clean Coal Central report published in August 2012. Please note the box at the top of your screen marked questions. If you have any during the presentation, submit those with your contact details. I will go through the questions, if any, at the end of the presentation. Coal is an abundant fossil fuel that currently accounts for almost 40% of the power generated throughout the world. Coal-fired power plants release to the environment sulfur dioxide, nitrogen oxides, as well as carbon dioxide and nitrous oxides, particulate matter, mercury, and other trace element pollutants such as cadmium, arsenic, molybdenum, selenium, vanadium, and various acid gases. Coal may contain as many as 76 of the 90 naturally occurring elements of the periodic table. However, most of those elements are usually present in only trace amounts, in the order of parts per million. Some elements have the potential to be hazardous, such as mercury, cadmium, or selenium, particularly if they are concentrated in more than trace amounts. Other trace elements may be concentrated in a specific coal bed, which may make the bed valuable resource for concentrated in a specific coal bed, which may make the bed a valuable resource for elements such as silver, zinc, or germanium. The affinities of trace elements for either the organic compounds or the minerals in the coal affect its quality. If trace elements are organically bound, then it is difficult to remove them from the coal by cleaning processes such as crushing or washing, which remove mineral matter from coal before firing it. Organically bound trace elements may be released only by burning or by deep chemical leaching, which is both very difficult and uneconomic. In contrast, trace elements associated with clays or pyrite may be removed to some extent from the coal by cleaning processes. Elements present in coal are divided into three groups. Major elements in coal are carbon, hydrogen, oxygen, nitrogen, sulfur. These occur at over 1,000 parts per million. Minor trace elements include coal mineral matter, silicon, aluminium, calcium, magnesium, potassium, sodium, iron, manganese, titanium. These may be present in concentrations between 100 and 1,000 parts per million. Trace elements, which are the constituents with concentrations less than 100 parts per million. These differ from one coal to another due to varying qualification processes, but identifying them allows the prediction of their release following combustion. For coal, the ash-forming elements, that is silicon, aluminum, iron, calcium, magnesium, and sometimes also the alkali elements, sodium and potassium, form the most important major elements. Trace elements cover roughly the whole periodic table of the elements after calcium, although the elements beryllium and boron should be included as well. A subclass of the trace elements are the heavy metals, with a density higher than 4 grams per cubic centimeter, such as cadmium, lead, mercury, zinc, and copper. Within the European community, the 13 elements of highest concern are arsenic, cadmium, cobalt, chromium, copper, mercury, manganese, nickel, lead, antimony, tin, thallium, and vanadium. Elements are also categorized as elements of major or greatest concern, which are arsenic, boron, cadmium, lead, mercury, molybdenum, and selenium. Arsenic, cadmium, lead, and mercury are highly toxic to most biological systems at concentrations above critical levels. Selenium is an essential element, but is also toxic above certain levels. High levels of molybdenum and boron in plants are also of concern. Molybdenum affects the lactation of cows, and boron is phytotoxic. Phytotoxicity is a term used to describe the degree of toxic effect of a compound on plant growth. Elements of moderate concern are chromium, vanadium, copper, zinc, nickel, and fluorine. These are potentially toxic and are present in coal combustion residues at elevated levels. Bioaccumulation is of some concern. Also, fluorine has an adverse effect on forage. Elements of minor concern are barium, strontium, sodium, manganese, cobalt, antimony, lithium, chlorine, bromine, and germanium. These are of little environmental concern. They are classified mainly on the basis that they are present in residues. Elements of concern but with negligible concentrations are beryllium, thallium, silver, and tellurium. These have non-documented relationships to health, but the low levels present are considered to have negligible impact. Radioactive elements, uranium and thorium, and the product of their decay are the natural radionuclides present in the environment. Of the naturally occurring radionuclides, radium, polonium, and radon are of some concern. Radium and polonium are alpha emitters with long half-life. Radon is a gas with a short half-life, and there has been some concern on the buildup of radon in underground coal mines. Environmental concern is based on non-toxic responses to high levels of trace elements. The responses to elements of major concern are summarized as follows. Arsenic is carcinogenic and can cause damage to peripheral nerves and blood vessels. It can also cause anemic and gastric disturbances. Arsenic is accumulated in the food chain, especially in seafood. Concentrations exceeding 50 micrograms per liter in drinking water are considered hazardous. Boron-rich soils can limit plant growth, resulting in decreased crop yields. Limits have been adopted on the permissible levels of boron in wastewater and water for irrigation. Cadmium has no known biological function. It accumulates in the kidneys and liver. It is carcinogenic and can cause emphysema and fibrosis of the lung. Chromium is also carcinogenic. It accumulates in the liver and spleen. Chromium exists in the non-toxic form chromium-3 and tends to be absorbed onto clays, sediments, and organic matter. It is therefore not very mobile in the environment. Chromium-6 is more mobile and more toxic. Fluorine is readily absorbed in the body and concentrates in the same tissues as calcium, especially in bones and teeth. There is some evidence to suggest that fluorine can cause genetic damage and disruption of the immune system. Fluorine causes leaf damage to plants. Exposure to mercury causes neural and renal damage and cardiovascular disease. Organomercury compounds bioaccumulate, particularly in fish. Pastures containing high levels of molybdenum cause disease in cattle and sheep, as well as poor growth and anemia. The high molybdenum affects the absorption and metabolism of copper, which is an essential element. Lead causes anemia and has cardiovascular, neurological, and gastrointestinal effects. Some compounds are animal and possibly human carcinogens. Although selenium is an essential element, the safe range is narrow. Elevated levels cause gastrointestinal disturbances, liver and spleen damage, and anemia. Average values of trace elements in internationally traded coals are listed in this table. Some trace elements are organically bound in coal, and many are associated with a mineral matter. For example, trace elements in U.S. bituminous coal were found mainly in the mineral matter fraction, while mercury, arsenic, nickel, lead, copper, and zinc in Australian coals were predominantly associated with sulfide minerals and organic matter. The amount of trace element emissions from coal combustion has been reported to be dependent on the modes of occurrence in the coal. Elements associated mostly with the coal organic and sulfide fractions tend to vaporize and then absorb on the fine particles when the flue gas temperature drops. On the other hand, elements combined mainly with the other mineral remain in the ash. One option for controlling the release and distribution of the latter is to remove them prior to combustion by coal cleaning. Pre-cleaning or washing the coal is a currently used method to reduce some trace element emissions. Trace element emissions from coal combustion have not been an issue of major concern in international or worldwide legislation. The main exception is the USA, which has recently adopted standards for mercury and other trace elements. There are a number of international and national agreements that aim to reduce trace element emissions, but very few of these have developed into limits on stack emissions in coal-fired power plant. In the few countries which have set stack emission limits for certain trace elements from coal combustion, these are generally met with existing air pollution control devices. The European Committee for Standardization, CEN 14385, is the European standard for the measurement of arsenic, cadmium, chromium, cobalt, copper, manganese, nickel, lead, antimony, thallium, and vanadium. The U.S. Environmental Protection Agency, Method 29, is a comparable multi-element sampling train used in the USA. Emphasis to date has been on the measurement and reporting of emissions of mercury. Currently, there is no international standards organization or CEN standard specifically for measuring selenium or other trace element emissions from stationary sources. However, A new work item has been opened up on this issue by the ISO in 2011, which would suggest that there is growing interest in trace element emissions, especially selenium. In the USA, the Clean Air Act amendments of 1990 identified 11 trace elements and their compounds commonly found in coal as potentially hazardous air pollutants. The emphasis on introducing trace element legislation began with mercury control. The 1990 Clear Act amendments required the U.S. Environmental Protection Agency to conduct an assessment of health and environmental effects posed by the emission of a range of trace elements from coal-fired power plants. Prior to the 1990 amendment, there were few data available on trace element concentrations and behavior in the combustion system. An information collection request began in 1999, authorized by the US EPA. This resulted in creating a database which today contains information on all US coal-fired utility boilers, coal analysis for mercury, chlorine, sulfur, moisture, ash, and calorific value, including 1,143 US generating unit, as well as air pollution control device inlet and outlet, flue gas analysis for total and speciated mercury for 84 of the above units. Numerous rules were developed and proposed since December 2000 pertaining to trace elements, mainly mercury, including in December 2011, the US EPA finalized the air toxics rule and promulgated the Mercury and Air Toxics Standards MATS rule, which imposed limits on the air emissions of mercury and other trace elements from coal as well as oil-fired power plants. In July 2012, amendments to the EPA rule were published, which included final limits for filterable particulate matter or total non-mercury hazardous air pollutant metals, or individual HAP metal limits for antimony, arsenic, beryllium, cadmium, chromium, cobalt, lead, manganese, nickel, and selenium. It is postulated that the MATS rule will require a minimum of 40% of all coal-fired power plants in the USA to deploy pollution control technologies to curb emissions of mercury and other air pollutants such as arsenic, chromium, nickel, and cyanide within 3 years. The US EPA estimated the rule would cost approximately $10 to $11 billion per year. The affected facilities include approximately 1,200 coal-fired units, representing about 45% of the U.S. electricity generation. Of these, about 50% fire bituminous coal, another 45% subbituminous coal, and 5% lignites. Trace element emissions from a conventional coal-fired power plant can vary by 3 to 4 orders of magnitude from day to day. This variability is due to many factors, including process conditions, such as the coal characteristics and furnace temperature, as well as sampling and analytical variability. A conventional 1,000 megawatt pulverized coal-fired power plant consumes over an average of 12,000 metric tons of coal per day and produces about 1 million metric tons of waste per year. The quantity of trace elements emitted from coal combustion in general depends on the concentration of the element in the coal, the physical and chemical properties of the element itself, the combustion conditions, and the type of emissions control technology used, and its collection efficiency as a function of particle size. Some trace elements become concentrated in certain particle streams following combustion, for example, bottom ash, fly ash, and flue gas particulate matter, while others do not. Various classification schemes have been developed to describe this partitioning behavior. Bottom ash is formed in the furnace. It is made from agglomerated ash particles that are too large to be carried in the flue gas and fall through open grates to an ash hopper at the bottom of the furnace. It is primarily comprised of fused coal ash particles. Bottom ash, which constitutes about 10 to 15% of the overall ash, has an appearance similar to dark grey coarse sand, and its particles are clusters of micron-sized granules up to 10 millimeters in diameter, 60 to 70% smaller than 2 millimeters, and about 10 to 20% smaller than 75 microns. One of the most common uses for bottom ash is a structural fill material. As many construction sites Large quantities at many construction sites, large quantities of fill are frequently required to level low places for construction and drainage purposes. Build embankments, fill trenches, backfill foundations, etc. The fill is typically local aggregate or crushed stone. Bottom ash is commonly used in these applications if it is available and close enough to be transported economically. Fly ash is one of the residues generated in coal combustion and comprises the fine particles that rise with the flue gas. In coal-fired power plants, fly ash is generally captured by electrostatic precipitators or fabric filters, depending upon the source and type of coal and its characteristics. The components of fly ash vary considerably, but all fly ash includes substantial amounts of silicon dioxide, both amorphous and crystalline, and calcium oxide, both being endemic ingredients in many coal-bearing rock strata. Fly ash, which constitutes 85 to 90% of the overall ash, is a fine, light grey powder made up of glassy spheres from submicron to more than 100 microns in size, 98% smaller than 75 microns, 70 to 80% smaller than 45 microns. Fly ash is suitable for utilization in industrial applications. Its constituents depend upon the specific coal bed makeup, but may include one or more of the following elements in quantities from trace amounts to several parts per million. These are arsenic, beryllium, boron, cadmium, chromium, cobalt, lead, manganese, mercury, molybdenum, selenium, strontium, thallium, and vanadium. The classification schemes generally make the following distinction between the elements. Class 1, elements that are approximately equally concentrated in the fly ash and bottom ash, or show little or no small particle enrichment. Examples include manganese, beryllium, cobalt, and chromium. Class 2 elements that are enriched in the fly ash relative to bottom ash, or show increasing enrichments with decreasing particle size. Examples include arsenic, cadmium, lead, and antimony. Class 3 elements which are emitted in the gas phase, primarily mercury, and in some cases, selenium. Classification of trace elements is connected to the concept of enrichment. The relative enrichment factor of an element in ash is defined as element concentration in ash divided by element concentration in fuel multiplied by the percentage ash in fuel divided by 100. Based on a pulverized coal combustion system with the dry bottom boiler and electrostatic precipitation for particulate control, for Class 1 elements, relative enrichment factor is about 1 for bottom ash and fly ash. For Class 2 elements, the relative enrichment factor is less than 0.7 for bottom ash and about 1.3 to 4 for fly ash. For Class 3 elements, relative enrichment is much less than 1 for bottom ash and much more than 10 for fly ash. Mass balance calculations based on the relative enrichment factor and trace element grouping during combustion is shown in this table. Control of Class 1 trace elements is directly related to control of total particulate matter emissions, while control of the Class 2 elements depends on collection of the fine particulate matter. Due to the variability in particulate control device efficiencies, emission rates of these elements can vary substantially. The volatility of Class 3 trace elements means that particulate controls have only a limited impact on emissions of these elements. Factors that influence the fate of trace element in coal combustion include combustion system design. This determines the fraction split between bottom ash and fly ash. Coal ranks and composition. This determines the mode of occurrence of the trace element species and their interaction with mineral matter transformations and partitioning mechanisms, and firing conditions and the level of equipment maintenance. Several studies consider that trace element release during combustion depends on the elemental form of trace species. This has an influence on its final partitioning. The more volatile elements seem to vaporize independently of mode of occurrence, and the char particle temperature determines the degree of volatilization. Elements that are more refractory show a greater dependence on mode of occurrence and char particle temperature on vaporization, and some post-combustion zone transformations have been identified which impact trace element partitioning. For example, The interaction of calcium with arsenic, selenium, and cadmium dictates that for coals which contain significant calcium oxide, the partitioning behavior of these elements is controlled by surface reactions rather than condensation. For a typical coal combustion plant, the most important gaseous species include arsenic as arsenic oxide, arsenic trioxide, and arsenic pentoxide, cadmium as elemental cadmium and cadmium oxide, chromium as chromium oxide hydroxide, dihydroxychromium or dioxychromium and chromic acid, mercury as elemental mercury, lead as elemental lead and lead oxide, antimony as antimony oxide, selenium as selenium dioxide, vanadium as vanadium dioxide, and zinc as elemental zinc. Cobalt, copper, nickel, and some of the chromium are not volatilized and found in the small particulate matter. Data indicate that temperature and not particle size dictates whether a certain trace element or trace element compound is volatile. For example, due to the lower temperatures in pressurized fluidized bed combustion and integrated gasification combined cycle, less trace elements are released compared to pulverized coal combustion, while a higher system pressure allows for a higher temperature for effective trace element removal by the particulate control device. Studies have shown that higher particulate removal temperatures result in lower concentration of trace elements in the fly ash. Stoichiometry, or the air factor, also plays an important role in trace element release, as many species are more volatile in a reducing atmosphere than under oxidizing conditions. 1 kilogram of coal will typically require 7 to 8 kilograms of air, depending upon the carbon, hydrogen, nitrogen, oxygen, and sulfur content for complete combustion. This air is also known as the theoretical or stoichiometric air. If for any reason the air supplied is inadequate, the combustion will be incomplete. The result is poor generation of heat, with some portions of carbon remaining unburnt and forming carbon monoxide instead of carbon dioxide. Coal cannot be burnt with stoichiometric quantity of air. Complete combustion is not achieved unless an excess of air is supplied. The excess air required for coal combustion depends on the type of coal-firing equipment. The presence of halogens, especially chlorine, can also impact trace element volatilization. An example of the partitioning of trace elements in a pulverized coal-fired plant with an electrostatic precipitator and spray dry scrubber flue gas desulfurization is given in this figure. The figure shows that about 90% of class 1 and 2 trace elements are collected in the fly ash, and that a significant part of the class 3 trace elements, approximately 17%, is captured in the FGD system. The investigation demonstrated that not all trace elements enter the system with the coal. Some boron was introduced in the water used to slurry the FGD sorbent. The FGD limestone introduced not only considerable amounts of lead and other trace elements such as arsenic, cadmium, manganese, but also iron, magnesium, silicon, and titanium. It is considered that in conventional pulverized coal-fired combustion with particulate control and a wet FGD system, the only species of concern are elemental mercury, mercuric chloride, selenium dioxide, boron trioxide, and arsenic trioxide. The remainder, which is 90 to 99%, which is mainly class 2 trace elements, are captured with the particulate control device. Experiments for a study were performed to find distribution of the arsenic, selenium, and lead after devolatilization. 3 bituminous coals from the eastern U.S. were selected and segregated into varying size cuts with different densities. The coal was then devolatilized and burnt under well-defined conditions. Char and ash samples were analyzed. A quantitative model was established and used to predict vaporization rates for arsenic, selenium, and antimony during coal combustion. The experimental results show that vaporization rate is proportional to elemental concentration. More elements are vaporized at higher pyrolysis temperatures and at higher combustion oxygen concentrations. Although the thermodynamic properties, such as the volatility of the arsenic, selenium, and antimony were very different, the fractions present in the vaporized or submicron particles were of the same order of magnitude. This was attributed to the association of the elements with the pyrite in coals. According to research, following coal combustion, the most volatile trace elements, mercury, selenium, and arsenic, remain mostly in the vapor phase as they pass through the heat transfer section of a boiler. The percentages of the total in-stack concentrations of these trace elements in vapor phase are reportedly chlorine up to 99% as hydrogen chloride or hydrochloric acid, fluorine up to 90% as hydrogen fluoride or hydrofluoric acid, bromine about 25 to 98% as hydrogen bromide, and mercury up to 98% as elemental mercury, mercuric oxide, and methyl mercury, selenium up to 59% as selenium oxide and selenium dioxide, arsenic 0.7 to 52% as arsenic oxide, and iodine 90 to 99% as hydrogen iodide. Based on the three classes of partitioning and enrichment behavior of trace elements presented earlier, this figure categorizes trace elements based on the volatility, in this case boiling point, and indicates the potential for their intermediate behavior. It shows that elements minor and trace, not vaporized during combustion, compose the matrix of both fly ash and bottom ash in the form of homogeneous melt as well as crystalline phases. Elements partially or fully vaporized undergo additional transformation and partitioning downstream as the flue gas cools down in the upper furnace and heat recovery section of the combustion system. The conversion of trace elements is determined by three complex and interrelated processes, including adsorption, condensation, and chemical transformation. Element mobility, in other words, element leaching from stored fly ash, has been the subject of many studies. Potential barriers to the use of fly ash from coal combustion have focused primarily on concerns about leaching of trace elements from the fly ash. In addition to the total metals content of the fly ash, the potential for leaching is influenced by the crystallinity of the ash. This is because crystallinity determines whether the metals are incorporated within the glass phase or within crystalline compounds which hydrate. The leachability of the traced metals, therefore, depends on the boiler design and remains relatively constant for a given source of ash. This is a view of two coal ash ponds in Skyland in the United States. As the caption says, the ponds can hold up to 450 million gallons of concentrated wet coal ash. A potential method for reducing trace element leaching in brown coal fly ash is the utilization of geopolymers, which are used for waste stabilization. They function in terms of encapsulation, which may be physical or chemical, and can provide acid resistance, compressive strength, durability, and thermal resistance. Synthesis of geopolymers involves using material with silica and alumina in the correct ratios, of course, and activated by an alkali metal hydroxide to produce a three-dimensional inorganic amorphous structure. Materials such as kaolinite, black coal fly ash, and waste slags, as well as aluminosilicate minerals, can be used as a basis for geopolymerization. Trace elements are released from both natural sources and human activities. As stated earlier, currently the trace element emissions considered to be of major concern are arsenic, boron, cadmium, lead, mercury, molybdenum, and selenium. Of these, mercury and lead are currently the trace elements of most concern with respect to emissions to the atmosphere from coal-fired power stations. Efficient particulate control devices capture the majority of trace elements in the fly ash. Electrostatic precipitators and fabric filter removal efficiencies are in the order of 99 to 99.9% for most trace elements, especially Class 1. For some Class 2 elements, the removal of efficiency is somewhat lower at around 95 to 99%, and even less for Class 3 trace elements. For trace elements associated with particles, the capture efficiency for any given particulate control technology should relate directly to the particulate collection efficiency of the system. Fine particles tend to carry more of the semi-volatile trace elements due to their larger surface area on an equal mass basis. Electrostatic precipitators have lower capture efficiencies for ultrafine particles, as smaller particles are more difficult to charge to a sufficient level for electrostatic collection. The problem is exacerbated with high resistivity fly ash. Particle agglomeration systems may provide an economical solution to fine particulate control from ESPs as well as fabric filters. Upgrading an existing electrostatic precipitator by addition of new electric fields or the use of high new frequency transformer rectifier technology or other advanced modifications could result in greater capture of trace elements. Replacing an existing electrostatic precipitator with fabric filters is another option, as the capture of the finer particles in fabric filtration is greater compared with ESP. The choice between electrostatic precipitation and fabric filtration generally depends on coal type, plant size, and boiler type and configuration. Both technologies are highly efficient particulate removal devices with design efficiencies in excess of 99.9%. Trace elements that are not captured in the electrostatic precipitator or fabric filter device may be removed by a downstream flue gas desulfurization system for SO2 control. The most widely used FGD system is the wet scrubber technology, followed by spray dry scrubbing and to a lesser extent solvent injection. These are discussed in detail in several IEA Clean Coal Center reviews. Combining a particulate control technology with FGD may assist in capturing further trace elements. However, some trace elements, including mercury, chlorine, selenium, boron, and arsenic, can still be emitted, as these are not consistently captured by the existing conventional air pollution control device. For example, arsenic flows in the environment in the EU were the subject of a study in 2007. Following investigative work at 2 coal-fired power plants firing approximately 60 tons per hour pulverized bituminous coal, it was found that about 94% mass of the arsenic in coal was captured in the ESP and about 6% in the spray-dry FGD scrubber. The arsenic concentrations in the bottom ash and the flue gas were below 1%, with a concentration of about 5 milligrams per kilogram arsenic in the coal. The arsenic input to the plant was about 300 grams per hour, of which approximately 1.5 grams per hour, that is about 0.58%, is emitted through the stack to the atmosphere. The arsenic concentration in the bottom ash, fly ash, and the FGD residues was about 5 and 30 milligrams per kilogram, respectively. International analysis of fly ash from coal combustion shows that arsenic is enriched, as with other trace elements, in the finest fractions which may not be captured by some particulate control devices. Selective catalytic reduction is the most widely used technology to reduce NOx emissions following combustion in a coal-fired power plant. These systems have been found to have some impact on mercury emissions, but the consensus is that NOx control systems have little influence on trace element behavior or removal. However, catalyst poisoning is a major issue in SCR systems, especially when firing coal with low calcium to arsenic ratio, which may cause rapid catalyst activation. NOx emissions abatement and control, including catalyst poisoning, is also discussed in detail in several IEA Clean Coal Center publications. In conclusion, trace elements that are vaporized during high-temperature coal combustion cannot be measured easily by available methodologies. Instrumental techniques have and continue to be developed to measure trace element concentrations online and in gas phase. Research continues, and in recent years more so, to improve understanding of partitioning between solid and gaseous residues of various trace pollutants during combustion for both cleaned and uncleaned coals. There's also increased emphasis on understanding and resolving the leaching issues of trace elements to water and soil from the coal, fly ash stored in landfills, and or use of byproducts such as gypsum, which are used in other industries. Areas that also continue to require further understanding include trace element speciation and enrichment in coal and coal ash, and the relationship between associated elements and coal macerals with mineral matter. Researchers agree that the quantitative relationship between trace elements partitioning in the fine particulate matter with trace element content from coal and other compositions with coal should be studied further. Finally, development of modeling can assist in predicting the status of trace elements in the combustion process and their partitioning following the cooling process in the flue gas. Modeling the mechanisms of transformation and control technologies for easily vaporized trace elements during combustion could also be useful to describe the transformation and mobility characteristics of the easily vaporized trace elements in the combustion process. Vaporization, nucleation mechanisms of trace elements such as retention by fly ash and reaction mechanisms of solid solvents with trace elements should be investigated further with an objective to develop multi-pollutant control technologies for trace elements as well as other pollutants with high efficiency and low investment costs. Thank you for listening. I'm going to check now if there are any questions and answer them if possible. Otherwise, I shall email you the answers. If you have any further questions, please feel free to email me. The next webinar is on the 13th of February by Andrew Minchner, talking about energy issues in Mongolia. I have a question here on saying, please explain the effect of furnace temperature on trace element emissions. As shown in the figure previously, as the temperature reduces, vaporization of the element is greater, and the smaller the particle, small particles have greater amounts of trace elements like mercury, arsenic, and selenium. I'm trying to go back to that, but the figure back, and I'm sorry, I can't find it right now. I will send you a detailed answer of the question. But let me see, differences between trace element emissions in combustion and gasification reaction. The report goes into detail about not just that, but the pressure as well in both the systems. Emissions of trace elements in gasification is less than emissions in coal combustion or pulverized coal combustion. That is based on measurements. However, the measurements, as I said, of trace elements is rather difficult. The methodologies are not available except currently for mercury. If I have answered that question, that's fine. Otherwise, please feel free to ask again, email me, and I will try to find greater information on the topic. But the report was on pulverized coal combustion as such, and the comparison was very quick. That's it. All I can say is thank you for listening, and again, as I said, if you have any further questions, please feel free to email me. So thank you, and have a good day.